Shall we start?
Yes, sir, we should start now.
Okay, sir. Manish, sir.
Yes, sir.
Shall we start, sir?
Yeah.
Okay, then, Rohit, sir, I would like to request you to please have some words for the Professor Manish Goswami, sir. Sir, please. Rohit, sir.
Yeah. Good morning, everyone. Happy Republic Day today. Uh, Today I have a privilege to introduce Professor Manish Goswami. Myself, Rohit, I'm Assistant Professor in Computer Science Department in IERT, Allahabad. Let me introduce Professor Manish Goswami. Professor Manish Goswami, the professor in Electronics Department in IIIT, Allahabad. He has experience of 18 years and he has a vast experience of the teaching, particularly the research area where he has worked is the analog and mixed signal VLSI design circuit, low power VLSI circuit design, data conversion, and digital design. He has already working on many projects, and some of the projects is sponsored by big agencies like DIT, Special Manpower Development Program, Chip 2 System Design, Low Power High Speed True Random Number of Generator for Cryptographic and Security Application. They are the main area where he had worked already, and he has already awarded with many prestigious awards, and he has 50 plus publications in the area of research. I would request Professor Manish Goswami to take over the presentation, and please, sir, come and.
So thank you, Dr. Rohit and Dr. Yatendra. Can I start?
Yes, sir. You may start, sir.
Okay. So I'll share my screen. So my screen is visible, I hope.
Yes, sir.
Okay. So good morning and happy Republic Day to one and all present over here. I am Dr. Manish Goswami. I am working as a professor in the Department of Electronics and Communication Engineering at Indian Institute of Information Technology, Allahabad, which is IIIT Allahabad. And as a program on this FDP, which is on recent trends of emerging research advances in design aspects and innovative modeling techniques with miniaturization for electronic devices and circuits. Today, I'm here to give you a presentation on the topic design of data converters for IoT-enabled smart system. So during this presentation, I'll be covering certain slides, which includes the introduction. Then I'll be focusing on the data converter, which is key to the Internet of Things enabled smart systems, design aspects, key components, results, conclusions, and finally some references. So this is the course of action which I'm going to cover up as far as my presentation is concerned. So we all know that today India is focusing very much as far as the Digital India program is concerned. Everybody might have seen these logos which stands for Digital India program. And there is hardly any particular field which has not been covered up as far as the Digital India program is concerned. So some of the pillars which the government of India has taken up as far as this Digital India program is concerned, or the promotion and investment as far as the Digital India program is concerned, is something which I am showing on the left hand side of this particular screen. And if you particularly see point number 7, it says about the electronic manufacturing, which means the government of India, or as part of the Digital India program, the government of India is focusing too much as far as electronic system design and manufacturing is concerned. And when it comes to something which is related to electronics, obviously the first question which comes is to design integrated circuits, to design integrated systems, and co-design techniques, which probably will give you the information about how this sort of a thing will come into picture. So as far as the electronic industry is concerned, the government of India has now started focusing too much as far as the electronic system designing is concerned. And I hope some of you might be knowing that recently Government of India has also announced the semiconductor policy. So as a result, there will be huge opportunities as far as the electronic manufacturing is concerned. Particularly as far as an IC industry is concerned, there is hardly any particular field which has not been touched as far as the IC industry in India is concerned. Right from consumer electronics to automobile electronics to medical electronics to wireline and wireless communication, in defense, aerospace, biomedical, everywhere you will find that the electronic industry has got its edge. And as a result, I'll just show you some of the graphs which I have taken from some of the reports. So according to the Indian Semiconductor Association, which has been generated by a Frost and Sutherland report, there are 3 domains which exist as far as IC designing or electronic designing in India is concerned. That includes embedded designing, VLSI designing, and in general hardware and the board designing. If you see the topmost graph, it says that the total semiconductor market has already reached its projected target. In 2020, it was expected that it probably will reach around $52 billion. And by 2025, it is expected that it is going to cross a 400 billion mark. So as a result, as far as the semiconductor design market in India is concerned, it's accelerating like anything. And if you talk of any particular VLSI companies in India, you will find that whether it is Qualcomm, whether it is NSA, whether it is Texas, NXP, Cisco, TSOL, Broadcom, every company has now started its operation as far as in India is concerned. Probably a company like Google also is now investing as far as semiconductor market is concerned. So that way, the private players, the government players, everybody is contributing towards making this electronic industry or semiconductor industry a larger. And there are certain categories which are driving the semiconductor market, which includes innovation with respect to analog circuits, the memory chips, discrete systems. Cryptography is something in which Government of India in particular and many private companies are investing, and of course ASIC is the market. And on the right hand side, on the left hand side, the top view, I am giving you one graph which gives you the distribution that the embedded market is now going to have its main advantage as far as the semiconductor market is concerned. In India, particularly, we can have or we can divide the chip industries among different sectors, which includes EDA company, a chip manufacturer company, a fabless company, a fabrication plant, IP providers, and ASIC vendors. So as far as an EDA vendors are concerned, these are called as electronic data automation vendors. They are not at all interested in fabricating any particular IC, but they provide you the tool by which you can actually fabricate some of the ICs. And standard EDA vendors are Cadence, Mentor, Synopsys, Xilinx, and so on. So all these companies are situated in India. As far as the chip manufacturers are concerned, again, Intel, AMD, TI, they have their own process, they have their own product cycle, they have their own fab plants. And in general, these chip manufacturers are also situated in India. As far as the fabless companies are concerned, they do not have any of the fab plants, but they contribute as far as making their own chipset and that sort of a thing is concerned, which means they own their own RTL. And Broadcom, Qualcomm, to name a few, are some of the fabless companies which are there in India. Till now, the fabrication plant was not there in India. For a small, for a small job like for fabricating some sort of an IC, we were to contact small countries which are even lesser than the state of UP or something like that. So either we have to contact Taiwan or Korea or these different countries as far as Europe and US is concerned. But now the fabrication plant has also been established in India, and now using 180 nanometer CMOS technology, it is possible to design a Make in India you can say a product, or we can actually have a fabrication plant in India, which is in Mohali, SCL Mohali. There you can actually, using an India chip program or using a special manpower development program, we can actually fabricate some ICs on 180 nanometer technology. So that was the space which was lagging in India, but now that has also been come up. In the other sector, which is an IP provider, ARM is something which probably contributes more. But as far as the other IP providers are concerned, those companies are also there in India. And for a specific task like some sort of application specific integrated circuit, which is called as an ASIC, there are companies like TI, IBM, NVIDIA, and so on. So all these companies are there in India, and as a result, you can say that the IC chip industry in India is have a huge market share. So that way, as far as this focus in the Digital India program is concerned, as I've already told you that electronic system design and manufacturing is something which is there in Government of India's vision. So as a result, to focus on this Digital India program, Government of India has already started this Make in India program. There is already a program on special manpower development program, which was initially from the simple manpower development. Then in the second stage, the Government of India has moved from chip to system design, and now Government of India in its third phase has now been able to shift from chip to startups. So now you will find that soon there will be a lot of startups which are coming in India as far as the semiconductor market is concerned. I've already told you that as far as the foundry work is concerned, India has already started fabricating an IC, and 180 nanometer CMOS fabrication plant is already there in SCL Mohali. There is already a policy on national policy on electronics. I hope some of you who are related to this field are already knowing that. And besides this, Government of India in the last month has recently introduced this semiconductor policy. So there are huge projects which are coming up as far as Indian market is concerned, and there'll be huge job opportunities as far as electronic manufacturing sector is concerned. So just for information, a project worth rupees 200 crores have already been set up. You might be knowing that few giants like Apple and other Samsung and other companies, they have already started their plant in India. FDI is already there as far as this electronic manufacturing is concerned. And besides a company like Qualcomm, Broadcom, Nvidia, Google, and so on, there are other companies which are also setting up their plants in India. So the next generation, which is surely on the electronic system design and manufacturing, you will find that most of the things which are coming up as far as these systems are concerned will be smart based systems. Many of us are already using a smartphone. So soon you will find that from smartphones, which is there in our hand, we'll be moving to a smart city, which has already been a concept. From there, we probably can move to a smart home concept, smart cars, and other sort of a thing is already there. So the next generation will be not only on building up some sort of an electronic systems, but to also make it a smart system. So I hope this particular image, some of you might have seen it. So can anybody let me know what this image is all about? Has anybody seen this particular image? If not, then I can provide you this information. So by looking at this particular person, I hope everybody may be able to guess that what that previous image is all about. So this is, we all know that it is nothing but an IT, you can say a magnet, IT giant, and it's called as Bill Gates. So Bill Gates is one of the person who has built up a smartest home in the world with the latest element of Internet of Things. And according to some of the reports which I have put it over here, you can see that each person in this house, as far as Bill Gates is concerned, has got a unique chip communicating with each and every equipment which is present in their home. So whether it is entertainment system, whether it is refrigerator, whether it is heating or cooling, or whether it is switching on the light or switching off the light. So all these equipment in his house is actively connected using some sort of a chip communication, and everything there in his house is basically a IoT based system. So that kind of an environment Bill Gates has already produced as far as his house is concerned, and that sort of a thing is probably going to come up as far as our future is going to come up. So the question which comes is, if I particularly talk of a smart home, because now this concept is coming up to to the reach of each and every people. So in the case of a remote smart home, automatically you will find that most of the devices which are situated at a different instant or different places are remotely controlled using some sort of a mechanism. And to have that sort of an environment, it requires that all the devices in the smart home are interconnected through the internet. So if that is going to be connected, as a result, you can easily control each and everything by sitting at a distance place also, and you can actually monitor the thing which is happening as far as your home is concerned. So this sort of a thing is now being come up as far as the future generation is concerned. And soon you will find that after 2 years or 3 years or something like that, you will find that most of the equipments in our homes are actually controlled by a small device like a mobile or something like that. So this is one example in which I mean, the house is connected using some sort of a different mechanism, and you will find that whether it is the antenna, whether it is the data, whether it is the computing network, everything will be connected using some sort of an equal device. As far as the definition of a smart home in particular is concerned, the smart home technology intelligently gives you the ultimate control over your homes by automating the lighting systems, dimming, blinds, electrical appliances, audio and security systems. The only thing is that as far as a smart home in particular is concerned, the thing has to be connected in a manner such that each device probably will have its own connection as far as internet is concerned. So using internet and using some sort of equipment, we can actually make such type of smart home. Why I've taken a smart home example? Because smartness comes from a home, and in general, a home is a place where everybody wants that. I mean, as soon as he enters a particular home, as soon as he enters his home, if the light is not operating at that particular instant, immediately as soon as he enter or she enters a particular room, the light should be automatically on. The thing, if he wants to see the TV, automatically the TV should be on as soon as he enters the room. And at the same time, when he leaves a particular room, all the devices which are connected should automatically be switched off, so that the power can be automatically saved and so on. So that way, a lot of things have been done as far as this sort of an environment is concerned. And one important thing, or one particular words which is being gathering a lot of attention, is IFTTT, which stands for if this then that, which means that the data which is collected from several sensors, okay, which includes humidity, temperature, ultrasonic, motion, and so on, can be accessed via if then that topology, in which internet, if it is not connected in this way, can be connected on that way, and so on. So there can be a lot of things which can be worked as far as building up a smart home is concerned. However, looking from the top of view, we can easily say that we can easily connect these equipments through internet and other sort of a thing. But what are the key modules which are required as far as bringing up any smart system is concerned? So there are three different modules which can be categorized as a controller module, a protocol of the transmission in which the devices are connected, and the different devices or the sensors which can actually connect to these different environments. So the controller modules, the protocol of transmission, and the devices and appliances are the three key components to build up any of the hardware which is required, or any of the system on a smart system is concerned. So why smartness? As I have already told you that consumer awareness is increasing, financial ability is there. Everybody wants a comfort in their house. Everybody wants that he or she should not every time go to the PlayStation and then play either a TV or say the speaker or something like that. Everybody wants a convenience. Everybody wants a security. So for all these features, and most important is that sometimes it happens that we forgot to switch off the electrical appliances and so on, which actually has resulted in a lot of energy wastage and so on. So all these smartness, if we can bring in our systems, then definitely and the systems can become a smart systems. So this is a picture of the automation market in India is concerned, and cities like Pune, Delhi, Mumbai, Hyderabad, all these places, this sort of a concept is increasing at a very faster rate. And some of these devices probably may be there as far as some of your home is concerned. Everybody, I hope most of the people are using some sort of a smart speakers. Amazon Echo is there, Google Nest is there, I mean, one of the most popular devices, Alexa. I hope some of you may be using. Some of you may be using a smart bulb and so on. So these are some of the smart devices which probably is there as far as our home is concerned. So the main challenge in connecting is not about how we actually connect different systems. The main thing is that if any of these equipments are placed near to the wall, or if any of the systems is placed in such an environment that proper signal is not being received as far as those devices are concerned, then sometimes the device becomes or goes to the passive mode, or in other words, that sort of a problem will irritate us the moment the signal may not be reached to that particular device. And normally what happens is that all these devices are placed near to the walls, and you already know that when there is a wall, automatically the signals may not reach exactly to that particular level had that been a device sitting at the middle of your home or middle of a room. So variable signal strength is something which is a problem as far as any device is concerned. And being a designer, our job is always to ensure that the signal strength in all these devices should be of such a nature that it should automatically get connected. But because of the placement, because of the placement of these devices in your homes, sometimes it may happen that one device may receive a signal in a very faster manner as compared to some other devices. So as a result, although in the picture it looks like that all the devices are equidistant, all the devices can be connected using some sort of an equal distance criteria. But if this device is connected to, or if this device is situated near the wall, or if this is near the wall, then sometimes it may happen that one device gets disconnected with other devices. So as a result, what will happen will be that we'll not be able to communicate with respect to those devices. So Intel has defined a definition of IoT in this particular fashion, that devices that are connecting to the internet and using some sort of a data analytics to extract valuable information. And as far as an IoT is concerned, or connecting of internet of devices is concerned, from IoT we can build up a smart home, from smart home we can build up a cloud, and if that sort of a thing is there in each and every home, then ultimately we can build up a smart city. So coming to the hardware, or coming to the technical portion of this, there are three modules which I have already conveyed to you. So one of the modules in any building of any particular device is its controller. The second portion is what sort of a processor or what sort of a controller you will be, microprocessor you will be using it. And the third module in any of the internet connected devices is how we are going to communicate with respect to these devices. Now, as I have already told you that the major issues in connecting any particular device is a variable signal strength. So if one device is connected or one device is situated very much near to that of the wall, automatically it may happen that the device may not be able to get a proper signal, which means variable signal is of course a problem as far as any device or building up any smart base systems is concerned. Now, most of the devices which are there are, digital in device, and in general, the signals which flows are always analog in nature. Or we can always say that the real world signals are always analog, whether it is temperature, whether it is pressure, whether it is voltage, and so on. All these sensors which picks up the signals are basically an analog devices, and they convert that particular signal to a digital device which is already there. So the first thing which causes a problem is that that particular sensor should be always in a position to pick up those particular signals. Now if your sensor is not strong enough, then it is going to create a problem. So to counter that, for example, if I take these different pictures, we can build up any IoT based system using these simple arrangements. You will have a microcontroller or you have a microprocessor, and all these different sensors will be attached to these microcontroller or to a microprocessor. So if you can see in this diagram, whether it is light, whether it is your music system, whether it is a temperature, all these things are connected using some sort of sensors, and from sensors the information will go to the microprocessor, or will go to your Raspberry Pi, or it will go to your device. So as a result, the sensor will collect some sort of a data, it will process that data, and it will make that particular results available to the world. So this particular diagram, which will give you the information about building up a smart system is concerned, is that using some sort of a data, we can actually process it with some sort of a processor, and that way we can communicate with respect to different devices. So as a result, we can build up a smart home, we can build up a smart infrastructure, we can build up a smart healthcare system, we can build up a smart transportation system, and in general, we can build up any given system. And Kevin Austin was the person who actually have coined this particular word. He told that Internet of Things is basically a phrase which is described as a system where Internet is connected to the physical world via some sort of ubiquitous sensors. So the key to any of these systems is a data converters, because as I've already told you that a sensor is something which picks up the signals as far as any smart system is concerned. It converts that signal to a digital one, it processes it, and then it sends the information to the next device. So if I talk of a general mixed signal system design, it consists of three different modules. It is the sensors which picks up the signals. Then that sensor converts that particular signal using some sort of an interface electronics, A by D and D by A converters. So sensor which is analog in nature picks up analog signals, and A to D converter converts that signal to a digital counterpart. Then it gets processed using some sort of a digital processing equipment, and finally it is being transferred as far as the actuator or the real world is concerned. So that way this whole process requires A by D and D by A conversion step, or it requires basically a data conversion step as far as building up of any smart based systems is concerned. And I have already told you that all real world signals are analog in nature, which can be a light, which can be a pressure, which can be a sound, temperature, and etc. And all these signals are converted by the A to D converter, and it being converted to the digital counterpart. So digital, why we convert it to the digital? Because in the case of digital processing, it is easy to process the data. The data will become a reliable. The noise will be minimum as far as the digital processing devices are concerned, like DSPs and other sort of a thing. And the data can be easily processed as far as that sort of a device is concerned. And once we do all these processing, we'll convert back that digital signal to that of the analog one using a D by A converter, and finally we send it to the real world. So as a result, the ADC will form the right component as far as any device is concerned. Or you can say that an ADC in general will be the first interface as far as any building up of smart system is concerned. So this particular slide on the left hand side will give you the information about the different types of applications as far as an A to D converter is concerned. So right from the instrumentation application to that of the biomedical one, to audio communication, to broadband, to ultra wideband RF communication, everywhere you would require an A to D converter. Because whether we are building a smart system which is catered to the application of a home, or we are building a huge transceiver system which probably can communicate from one city to the next city, ultimately we'll be requiring a to D converter at each and every stage. But that depends upon for what frequency we'll be designing it. So right from 100 hertz to that of 1 kilohertz to that of 10 kilohertz to up to 1 gigahertz, we can have different types of an ADCs. And as I've already written that depending upon the applications, we can have different types of an ADC. So flash ADC is normally used for a very high frequency application, pipelining or the interpolating, or in general for a broadband wireless communication, we go for ADC. Normally for speech, audio, and other sort of applications, even for biomedical, we go for sigma delta, SAR type of an ADCs and so on. So this particular chart on the right hand side will give you the information about the different types of an ADC which are required as far as any device is concerned. And they can be classified among different categories which include speed, resolution, as well as area and power consumptions. So if you see this particular graph, you'll come to know that a flash type or a parallel type of an A to D converter is that particular A to D converter which has got a very higher speed. But since in building up of any electronic system, building up of any semiconductor system, we always target towards three criteria, which is speed, power, and chip area. So when it comes to speed, we'll always have a flash type of an ADC, but the disadvantage of this is that it occupies a larger chip area. So that way, when area is our main concern, we probably will not go for a flash type of an ADC, rather we'll go for either pipeline or SAR type of an ADC. But the disadvantage of SAR type of an ADC is that the speed is lower as compared to that of the flash type or the other pipeline type of an ADC. So as a result, depending upon the applications, we actually can choose any type of data converters, which can be a successive approximation register called as a SAR. We can go for a pipeline, we can go for a flash, or we can go for some other architecture. And this particular chart will give you the information about the speed and the resolution. So if you go for a flash type of an ADC, automatically you will find that it has got a highest speed. And because of the disadvantage of the chip area, we normally restrict it to 4 to 6 bits as far as conversion of analog signal to that of the digital is concerned. However, if I want some other application in which area is not my issue, then I can, or speed is not my issue, then I can go for any of the ADCs which I have written over here. Okay. So in order to find out whether my ADC is working fine or not, or what its power dissipation all about and so on. So this particular chart will give you the information about the figure of merit of any A to D converter is concerned. There are two types of figure of merit. One is called as Shearer figure of merit, and one is called as a Walden figure of merit. And this particular chart will give you the information that the figure of merit is coming somewhere around less than 10 or less than 1 as far as the latest trends in digital domain is concerned. So you can very well Google and find out that what is the latest scenario as far as the figure of merit is concerned. Now coming to the semiconductor roadmap, we already know that the chip fabrication nowadays which is happening at a very lower technology, which means when we started from say a Pentium processor which was somewhere around 500 nanometer. So from 500 nanometer we moved to 350, from 350 we moved to in between 240 or 220 also. From there we moved to 180 nanometer CMOS technology. From 180 we have moved to 120, from 120 we have moved to 90 nanometer, then to 65 nanometer, then to 45 nanometer, 32 nanometers and so on. Even product, I hope some of you may be knowing that a 7 nanometer product is also there as far as a company like Broadcom, Qualcomm and other sort of a thing is concerned. So proof of concept it has already been established as far as a 3 nanometer or 7 nanometer product is concerned. So everybody now is miniaturizing the things. Everybody is trying to have a lot of features as far as a given small space of silicon wafer is concerned. And everybody is also working towards making this parameter, which is power supply, to be as minimum as possible. Because out of three areas, which is speed, power, and chip area, everybody wants that the power dissipation of my device should be as low as possible. No, everybody might have seen that if you talk for half an hour or so, or if you work on say 30 minutes, 40 minutes, and so on, as far as a laptop is concerned, you normally feel that that particular device is becoming a little bit hot. Or if you talk for around half an hour or so, sometimes your mobile device becomes a little bit hot. So nobody wants that his device should dissipate more amount of power. So out of speed, out of power, out of chip area, even if your chip area increases by 100% or 10%, even if you take 1 nanosecond more to turn on your TV and something like that, that does not bother you. But at every 1 nanoseconds, if you see that where is my plug-in point, I have to charge my device and so on, then automatically it will be a problem. So as a result, everybody is now working towards a low power, or everybody is designing a circuit which is operating at even 0.6 volts, 0.5 volts and so on. So this motivation that why people are going for a lower power supply, what is the size of this particular IC? So this particular chart will give you the information that even it is possible to hold a IC in our fingertip. The size of the IC has become so small that it is possible that we can accommodate more than billion transistors as far as placing that particular IC in our hand is concerned. And when I say that I'm working on 90 nanometer, when I'm working 100 nanometers and so on. So you can very well think of that what sort of a small dimensions that particular IC probably would be giving you. So on the left hand side, this chart will give you the information that the size of an IC is almost comparable to that of the size of a particles or micromolecules or more molecules and so on. And if you see particularly the example of a human hair, so the thickness of a human hair is almost around 100 micrometers. So the IC has, the size of a transistor has gone to 1000 times that of the human hair also. So that motivates, the VLSI designer to work on such a challenging task and to design an IC as far as that sort of a thing is concerned. And Murray's law was something which is still holding true as far as designing any sort of an IC is concerned. So the concept of very large scale integration starts from here. It is a process of creating an integrated circuits by combining the thousands of transistors based circuits into a single chip. So basically what will happen in the case of a VLSI, which stands for a very large scale integration, is that millions of electronic components will be placed in a single silicon wafer, and everything will be connected as far as their interconnections is concerned. However, to build up any of the VLSI systems or to build up any system which requires an electronic manufacturing or IC designing and so on, there are 5 things which rules the market. So one thing is called as a circuit speed, one thing is called as a power consumption or power dissipation. The third thing is a design area. The fourth thing is time to market, and fifth thing is cost. Which means whenever any designer takes up any task of designing any of the ICs or semiconductor products, he or she should always think of these 5 dimensions. Which means how to make a device to work at high speed, or how to make it as fast as possible. Nobody wants that if he is pressing the remote button of a TV today, the channel should get upgraded tomorrow. Everybody wants that immediately on pressing the remote button of TV, immediately the channel should change, which means everybody wants the speed of a device to be as high as possible. At the same time, everybody wants that the power consumption or the power dissipation should be as low as possible. I've already given you the example that nobody wants that his device should become hot or it should dissipate power, so that every time he or she should see that where is the plug-in point and he or she should charge this particular device. At the same time, everybody wants the chip area to be as low as possible. Already a product on 7 nanometer, 10 nanometer is already there, because if a device occupies a very small area, then it is possible that within a given silicon area, I can have more features onto that. At the same time, everybody wants that the time to market of that particular product should be as fast as possible. Already you know that a lot of mobile phones are there in the market, lot of devices are there in the market. So how fast you can bring up that particular thing to the market is also something which is contributing as far as the semiconductor market is concerned. And particularly how cheaply you can bring up that particular product into the market is something which is also countable. So these 5 parameters rules the VLSI industry in India and in general the semiconductor situation all over the world. And these are the 2 persons who actually have started this concept of integrated circuits. So Jack Kilby and Robert Noisy are the person who actually have started working on these integrated circuits. So complexity of chip is concerned, we already know that we can introduce this with respect to the transistor counts. So already you know that 2 billion transistor count has already been reached as far as Intel Itanium processor is concerned. And the same thing can also be correlated with respect to the DRAM chips, which means how things we can bring up as far as our memory is concerned is something which probably can be counted as far as DRAM capacity is concerned. So it is possible to have all the books, it is possible to have, even an encyclopedia as far as your device is concerned. So there are different ways by which we can design some sort of integrated circuits. So people can work at a circuit level, the people can work at a gate level, it can work at a module level, and system on chip concept is already there as far as the design exception level is concerned. Now, in the last slide, I told you that there are few parameters like speed, chip area, power dissipation, and so on. Now, if you work at a certain level, then only you can actually control those parameters. Which means if you work at a module level, or probably if you work at a gate level designing, it may not be possible to actually control the speed, the power dissipation in the chip area to the fullest extent. However, if you work at a circuit level or if you work at a transistor level, then it is possible to control all the three parameters, which is speed, power, and chip area. Okay, so all the three parameters can be fully controllable the moment you work at a circuit level or the moment you work at a transistor level. Now, to a designer, a lot of transistors are being available. He can design the circuit using CMOS. He can design the circuit using BJTs. He can design the circuit using, you can say in general, a bipolar and unipolar device. Within that bipolar and unipolar also, he can design a PNP based transistor. He can design the circuit using NPN transistor, or he can design using an NMOS, PMOS. A combination of that can be a CMOS, transmission gates, and so on. Even SCRs and PNPN and other sort of transistors are also available. Which means that to a designer, a lot of flexibility has been given. That is, whether he can design the circuit using BJT, or he can design the circuit using, say, a MOS, or within MOS, can he design the circuit using only exclusively NMOS, or using PMOS, or using a combination. So it always depends upon for what application you are designing that kind of a circuit. If power is your main criteria, then always you have to design for a CMOS based circuits, because CMOS dissipates low power in comparison to that of the BJT or a bipolar device. However, if you want speed to be higher, then instead of a MOS, you have to go for a BJT based transistors, or you have to go for a BJT based circuits. So depending upon that kind of a topology, or depending upon the application within NMOS and within PMOS, or within PNP and within NPN, it is always an NPN or it is always an NMOS, which has a higher speed as compared to that of the PMOS based circuits. So depending upon whether you want the speed to be higher, whether you want the power to be minimum, you actually have to choose some sort of a device. And that is what we have to tell to each and every person who is actually working as far as this sort of a field is concerned. So if you want the power dissipation to be controllable at a designer's hand is concerned, if you want to control the speed, if you want to control the chip parameters, chip area, and so on, so all these parameters can be controllable the moment you are going to work as far as your circuit level designing is concerned, or your transistor level designing is concerned. So if somebody says that I'm working at a transistor level, this means that all the three parameters, which is power, which is speed, and which is chip area, can be easily controllable the moment you work on a circuit aspects. And how we can control it? By controlling actually the width and length of that particular transistor. Which means if I control the aspect ratio, which is also called as the width and length of that particular transistor, if I precisely control the width and length of the transistor, I can actually control all the three parameters. Okay, so this is something which I thought that can be discussed with you all. So the key component, again coming back to this one, which is the diagram which I've shown you, in order to build up any of the smart system, is a problem which is with respect to a variable signal strength. So it may happen that if you are working on some sort of building up any device, if you are having a fan, if you are having a tube light, or if you are having some sort of a sensors, for example, in this particular side, you have an IR sensor, you have a smoke sensor, you have an AC sensor, you have a gas sensor, you have a temperature sensor, you have a light sensor, and so on. So all these signals which are being received by these particular sensors, it may happen that IR sensors may receive a signal much easily as compared to any other sensor. Or say, for example, the first three sensors receive the signals in a good manner as compared to rest of the three signals. So if there is a problem of receiving the signals as far as any particular device is concerned, then it is going to cause a problem. So that way, the ADC may not be able to convert that particular signal to the equivalent digital part. And if the gas sensor, for example, if not able to send proper information to the A to D converter, the microcontroller sitting over here may not be able to convert that analog signal to that of the digital counterpart, and then correspondingly it will not be able to send this information to the outside world. So variable signal strength is the main problem as far as connecting any devices in a smart system is concerned. So in order to bring up any performance parameter as far as an A to D converter is concerned, there are 6 parameters which are mainly contributing, which are resolution, sampling rate, power dissipation, speed, static and dynamic parameter, and the 6th one is called as a chip area. And a combination of them is sometimes defined with respect to figure of merit. So for what resolution you are designing a circuit, what should be the sampling rate, how much power dissipation your device is going to dissipate, what is the speed of it, what are the static and dynamic parameters, and what are the chip areas. So these 6 or 7 different 6 different parameters decides that whether the ADC which you have designed is really working fine or not. And a combination of speed, a combination of power dissipation, their products and so on will give you one quantity which is called as figure of merit. So coming up to the different types of an architecture as far as an A to D converter is concerned, these are some standard topologies which includes a flash type, which includes a SAR type, which is called as successive approximation register, a binary search ADC, and a time interleaved ADC. This is a newest concept as far as a binary search is concerned. In the previous literature, you can find that a lot of work has already been done as far as a flash ADC is concerned and SAR type of an ADC is concerned. So if you see this particular diagram, what you're going to see is that as far as a flash ADC is concerned, every comparator, COMP stands for comparator, every comparator is arranged in a parallel fashion. So when any job is being distributed in a parallel fashion, if I do certain work at the same time, if you do certain work at the same time, if third person does the same work and so on and so forth, or part of the work, then automatically the efficiency of that work normally increases. So whenever you go for any parallel combination architecture or whenever you go for any parallel structure, automatically the output is generated in a very faster manner. But the drawback is that in that case, a lot of persons will be involved. If I give you the same example, that half of the portion I am doing, 1/4 of the portion you are doing, 1/8 of the program somebody else is doing, and so on. So that way, all the persons will be engaged, and that way, the resource utilization will be more over here. So in terms of VLSI, we say that the power dissipation will be more because each and every person will be involved in that particular task. However, the advantage will be that in such a scenario, we'll be able to get the output in a very faster manner. So although speed of finishing up that particular job will be faster, but at the same time, everybody will be involved in doing that sort of a job. So flash ADC is something which executes the output in a very faster manner. But when it comes to the power dissipation, due to 2 raised to power n number of comparators, normally what happens is that it dissipates more amount of power. So the other counterpart is called as a SAR type of an A to D converter, which uses a single comparator. If you can see over here, it uses a single comparator. So at each and every case, although it is going to dissipate lesser amount of power, but at the same time, the disadvantage will be that it will not be able to generate the output in a single clock cycle. So that way, although one is giving you the advantage of speed, the other is giving you the advantage of power, but at the same time, each of them is giving you certain disadvantages also. And if some particular task is not able to achieve in given time frame, what we do is that we go for a time interleaving approach, in which we distribute the work to some of the tasks, to distribute the work in some of the tasks, and so on, and we combine them to achieve a single output. So a new entrant was, or in the research community, people thought that why not to introduce an architecture which will give you the higher speed of flash, and at the same time it will give you a lesser power as far as a SAR ADC is concerned. So the amalgamation of flash and SAR was a result which was named as a binary search ADC, which if you can see over here uses less number of comparators in comparison to the flash, and at the same time it gives you less number of, or it gives you dissipates lesser amount of power. So using that sort of a concept, we actually have started working on designing a flash ADC with a reduced comparator architecture, and we utilize this concept of SAR ADC and flash ADC in a single architecture. So it was giving us a speed as comparable to that of the flash type, and at the same time it was dissipating lesser amount of power, and at the same time it is giving us an advantage with respect to both the ones. So as a result, we thought of a new architecture, and that was using some sort of multiplexers and a combination of comparators. So that was some concept which we thought that probably will work, and we succeeded in that also, because that sort of a work has not been established at that particular time. So somewhere about 2013 and 14, we started building on a designing of A to D converter using a concept of digital as well as analog contribution in a single structure. So the MUX, is basically a digital device, and a comparator is basically an analog devices. So using a combination of comparator and multiplexer, we actually have designed a 4-bit ADC, if you can see over here. And what we did was that, for example, if I say that I have a range of numbers, say from 0 to 100. Suppose I tell you that within 0 to 100, I have, you can thought of some number, and I'll give you that what that particular number is about. Suppose, for example, you thought of some number like 99. So how I am going to find it out? One way is that I can, simply ask you that whether the number is between 0 to 10 or 10 to 20 or 20 to 30, 30 to 40, and so on. So when the numbers, you say that, okay, I have thought of the number as 99 and it is coming from 90 to say 100, then immediately in the next step, I'll say that whether the number is from 90 to 95 or 95 to 100 and so on. So by doing that sort of an iteration, I can actually find out that, that you have thought of the number as 99. If you are following that sort of a topology, it is basically a flash type of a topology. However, what alternative way I can do is that I can divide this range in each iteration to half of that value. For example, in the first instance, if I say that if you have thought of the number as 99, then I can immediately ask you that whether the number is between 0 to 50 or from 51 to 100. So you will say that, okay, my number is say between 50 to 100. Then immediately I'll further, break the value between 50 to 100 as its mid value being 75. So I'll be asking you whether the number is from 50 to 75 or 75 to 100. So you will say that my number is from 75 to 100. Then immediately I'll be asking you that whether the number is from 87.5 to 100 or from 75 to 87. So which means on each iteration, I'll be asking you whether the number lies between the mid value of two numbers in which bins and not. So depending upon your answer, I can then find out, okay, that your number is taking that much, that your number is actually this sort of a thing. So at each clock cycle, I'll be dividing the whole base among half, and then correspondingly, I'll be doing the same sort of a job. So that sort of an operation we adopted as far as this flash and reduced comparator architecture is concerned. So if you can see, the first comparator is comparing the input value with respect to half of that value. In the second comparator, it was 1/4 and 3/4, which means 1/4 corresponds to half and further half of it, and 3/4 corresponds to more than 50% of that value with respect to 100%. At each iteration, we are dividing that value by half, 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 and so on. And ultimately, eventually, we'll be able to get a particular digital counterpart depending upon that analog value. However, later we found out that, actually, if we design an A to D converter, then if we place that A to D converter with respect to any equipment or with respect to any device, the problem of variable signals was already there. And I hope everybody might have seen that if you go to the top of a hill, or if you go to, say, in a lift and so on, normally the signal is something which you not receive in those scenarios. If you are moving in a lift, sometimes the signal get disconnected. So we thought that why not to have a variable block, or why not to design a variable resolution ADC, which probably will increase or decrease the strength depending upon the signal value. So what we did in the next stage is that we have combined a different two-stage A to D converters, and depending upon the signal strength which was coming up, we actually have designed a variable resolution block. So that variable resolution can work with respect to 2 bits also, and it can work with respect to 8 bits also. If the signal strength is quite high, probably I'll be going for a 2-bit combination. And if the signal strength is quite low, then in that case, I can go for an 8-bit. So that way, if my structure gives me a variable resolution architecture, then at certain times I can save a power also, and at certain times if the signal strength is too low, then in that case I can combine all the stages together and I can have a higher resolution ADC. So this concept we utilized, and then based on this we actually have designed different types of A to D converters. So this is the block diagram of a 2-bit A to D converters, and if you can see over here, in the first case, the value is divided with respect to, compared with respect to half of that value. So the value can be half, greater than half, and the value can be lesser than half. So if the value is lesser than half, then this V reference by 4 will be selected. And if this value is greater than half, then 3 V reference by 4 is selected. So that way, depending upon a simple topology, we can actually design an A to D converter. And using the same concept, we can actually design a variable resolution A to D converter. So this concept we started, and we then solved some problem with respect to the variable signal strength also. This is the schematic diagram of a comparator. So probably in the second half you have some lectures from other faculty. So probably they'll be telling you more about the comparator architecture. So as a result, we already have told you that we thought of some new architecture, that why not to combine the advantage of flash type ADC and SAR type ADC in a given structure, and ultimately we land up in a binary search ADC architecture. So in the case of a binary search architecture, although it uses n number of 2 raised to power n number of comparators, but we thought that why not to utilize that comparator which is not being used. So if I give you the same example, that if the number is say from 0 to 100, if my range is say from 0 to 100, and suppose you have thought of the number as 99. So the first question which I'll be asking you is that whether the number is from 0 to 50 or 50 to 100. So if you say that the number is from 50 to 100, this means the next comparator will be with respect to what? It will be with respect to 75, which means this lower comparator will never be utilized in my designing, or it will be unutilized as far as my whole designing is concerned. So we thought that if some comparator is not being utilized and it is occupying a certain area, why not to reuse as far as the same concept is concerned. I hope you will be getting it. That again, I'll tell you that if I give you the number say from 0 to 10, and if I tell you to think of any particular number, okay, suppose you have thought of the number as 7, then my job is to find out that whether the number which you have thought of is 7 or not. So how I can do, I can in the first clock cycle or in the first instance, I can ask you that whether the number which you have thought of lies from 0 to 5 or 5 to 10. So if your number which you have thought of is 7, definitely you are going to tell me that the number is from 5 to 10, which means the lower value of 0 to 5 will never be utilized as far as your structure is concerned. But somebody may think of the number as 3 or 2, which means in my structure I have to give a provision for a sequence of steps in which 0 to 5 is also there, 4 to 10 is also there. So we thought that why not to reuse the architecture in order to find out some sort of an A to D converter. So if say I'm going by the upper path in this fashion, then this lower path will remain unutilized. So why not to reuse this concept as far as building some sort of an architecture is concerned. So we then introduced that sort of a concept as far as the binary search ADC is concerned, and we then recently published an architecture in 2020, which is an analog integrated circuit and signal processing, which was using the concept of reusability. Which means if I'm going in the upper track, half of the number, which is 8, 12, 14, 16, and so on, then if I'm using this upper concept, so if I'm going by the upper path, then there are certain comparators which probably will not be used as far as the lower comparator is concerned. So here the example is say from 0 to 16. So if I'm going from 0 to 16, or if any number can be from 0, then 1, then 2, then 3, then 4, then 5, 6 on till 15. If I'm giving some sort of a flexibility in choosing that number. So suppose you have thought of the number as 13. So 13 means firstly I'll be asking you whether the number is between the mid value or not, which means V8. So once it is V8, then I'll be asking you whether the number is say between 12 to 16 or not. Then I'll be asking you whether the number is greater than 14 or not. And then you will say that no, my number is 13, which means I can get somewhere over here. which means firstly I'll ask you about whether within the range of 0 to 16, whether the number lies above half of 8 or whether it is lesser than 8. Since you have thought of the number as 13, you will say that it is greater than 8. Then I'll be asking you that between 8 to 16, the mid value is 12. So I'll be asking you whether the number is from 8 to 12 or 12 to 16. You will say that no, it is greater than 12, which means again I'll be asking you the mid value, which is 12 to 16, which is 14. So I'll be asking you whether the number is between 12 to 14 or 14 to 16. Suppose you have thought of the number as 13, so you will say that no, it is lesser than 14. So since it was greater than 12 and lesser than 14, hence the number comes out to be 13. So that way, this way, I'll be progressing towards the upper path, which means the lower comparators will remain unutilized. These comparators will remain unutilized. So while finding out the last value, I'll be again using this comparator, which I have not used in the previous instance. So this concept we have utilized designing, and as a result, we actually have got some fantastic results. So if you see that this is an example of a range of numbers, say from 0 to 1.8 volts, and for an input of 787 millivolt, firstly I'll be because my range is from 0 to 1.8 volts, the mid value is 900 millivolts. So since my number is lesser than 900 millivolts, the comparator will give me a value as 0. I'll be getting the first digital bit as 0. Then I'll be finding out the next input, which is 450 millivolts. So I'll again be comparing whether my number is, say, between 450 millivolt to 900 millivolts and so on. Since your input is higher, 75857, you will be getting the output as 1. So you'll be getting the output as 1. Then I'll be comparing with the next of the value, which again will come out to be 1, and then finally the value will come out to be 1. So that way the 787 millivolt input, which is analog in nature, will be converted to the digital counterpart as 0, 1, 1, 1, and so on. So this is how the analog to digital conversions can be taken place with respect to reusability concept, which has recently been introduced as far as this designing is concerned. And for some of you who probably are faculty members and who are interested, or whose students are interested in doing some sort of a research work, I invite all of them to kindly contact me so that we can have some sort of a joint research also. In IIIT, we have a PhD working professional programs also, which means for those aspirants who are interested in doing research and are working somewhere else, not in Allahabad, can join a PhD program under the PhD working professional schemes. So a lot of flexibilities we are offering as far as generating some sort of a research environment is concerned. So we then tested this 4-bit ADC, and if you see over here, for a ramp input which covers, say, from 0 value to that of the farthest value, for each and every bit we are getting a corresponding digital output. This is the simulation waveform for an 8-bit variable resolution ADC, which means depending upon the type of the signal value which we are getting, we can actually get all the different values. I hope some of you may be knowing that for fabricating an IC, we requires a layout, and that layout is only the thing which we send to the foundry for fabrication. So this is how the layout is being created as far as, or we have created for the case of a variable resolution ADC. And on putting it on a 500 nanometer IC pad frame, we got this particular diagram. So on the right hand side is an IC's diagram, microscopic diagram, in which we have substituted this variable resolution ADC and in general a 4-bit ADC. And we have tested this also using some sort of an equipment that we have tested in one of the company at Noida. And we got those testing results also. So this is the result which I have got as far as the testing for that variable resolution A to D converter is concerned. So the big question which comes is that how we are actually designing an IC. So there are certain steps which are to be required. The IC can be digital in nature, the IC can be analog in nature. So if it is a digital based IC, or if you are working on an analog based ICs, the first thing in any case, whether it is digital or analog, is to draw some sort of a specification. For a certain specifications only, we actually design some sort of an IC. So depending upon the specification, we choose a circuit. So as I already told you that whether you are interested in speed or whether you're interested in power or whether you're interested in some other criteria, we actually choose some sort of transistors. It can be an NMOS, it can be a PMOS, it can be a CMOS, it can be a PNP, it can be an NPN, it can be a combination of bipolar with respect to CMOS, which is also called as a bi-CMOS ICs. So depending upon the type of the application which you have thought of, depending upon the specifications, we choose a certain circuits, or we actually design a certain transistor. Designing means actually calculating the width and length of that particular transistor. Then we do a simulations. Once in the simulation everything is coming out to be a correct one, we go for next step, which is called as a physical designing, or which basically is called as the backend designing. That is that is how the structure looks like in a physical manner, what should be its width, what should be its length. So all these things are required as far as physical designing is concerned, and you will find that most of the electronics engineers probably do a very good physical design, and there are different tools which takes care of that. Now the ICs are coming up at a very small scale, or you can say that a very 7 nanometer, 10 nanometer, even 45 nanometer or 32 nanometers ICs are coming up, and within that small space we have to make some sort of a connections and so on. So which means that the physical drawing which we are doing for that particular transistor, whether that particular transistor is behaving like a short circuit or not, or how much minimum distance you have to keep, all these things probably will be taken care by one important parameter which is called as a DRC, which stands for design rule check. And for any of the ICs in which you are interested to fabricate, you have to first get a value for that DRC. Or DRC file will provide you the information that you have to place a minimum gap of say at least this much micrometer or nanometer length from one metal layer to that of the next metal layer. If I'm making a connection, or if I'm making a contact of one metal layer with respect to another metal layer, what should be the contact width, what should be the contact length, what type of the contacts you will be using. So all these informations are available in one of the files which is called as the DRC file. Whenever you are interested in sending your IC for a chip fabrication, your IC designing, physical designing should be a DRC clean file. Then you go to the simulation of that, which is called as a pre-layout simulation, and finally you do a post-layout simulation. Then you do some sort of checkings which with respect to the clocks, with respect to power and other sort of a thing. You also extract some parameter called as RC extraction, which stands for resistor capacitor extractions. You do certain checks, and finally when everything is completed, you do a step which is called as a DRC and LBS, which stands for a layout versus schematic, which means the layout which you are drawing is really the layout for that schematic or not, or for that circuit or not. And then finally you compress every information in the form of some graphical streams called as GDS or Siltec and so on, and then you send this information to the foundry. So once a foundry receives that information, it gives you the IC back, which actually you can later on test it. If you're working on a digital IC, then the first step there will be called as hardware description simulation, which is called as an HDL simulation. Then you'll be writing different codes as far as an HDL is concerned. Some of you may be writing a code on Verilog, some of you may be interested in System C, System Verilog, or VSDL and so on. So there, if you are interested in digital IC, you will be writing some sort of a code. So already on the left hand side, I've written a small code, which is this one. So this is the first step. Then you do a simulation that whether the code which you have written is correct or not. Then you do a high level synthesis, which means it converts your RTL to a gate level netlist. So everything code which you have written will now be converted to the gate level equivalent diagram of it. Okay, so that will be called as a synthesis, which converts your RTL to the gate level netlist. Then you do a step which is called as physical designing, which already I have told you in the previous slide. So you actually find out the width, length, and so on, and you actually create a physical designing of it. And finally, you send your design to the fabrication. So if you see this particular circuit, so this particular circuit is a circuit which is commonly called as an inverter. If you give an input X to it, you will be getting an X bar, and it consists of two transistors, which is a PMOS over here and an NMOS at the bottom side. This is a circuit diagram which we have done, okay? And the equivalent layout of this particular diagram looks something like this. So what we do is that we send actually this layout to, we actually draw this step which is called as a physical designing, or how physically this PMOS and this NMOS looks like is something which probably is shown as far as this circuit, this physical diagram is concerned. So this VDD will be a blue colored one. This ground will be, or VSS will be this blue colored one. This input which is coming, or the gate terminal of this transistor will be is showing by a red color. It stands for I mean a polysilicon. It's called as normally. The connection from drain to the drain of an NMOS is connected in the blue diagram, and so on. So you draw this sort of a diagram, and what you see inside an IC, or I've drawn this particular diagram. In this diagram, or in this diagram, which is the inside of an IC, if you zoom it, what you're going to see is that you will be going to see this particular diagram only. In fact, when we fabricated our first IC, we are also not knowing that the same diagram is going to come up or not. But later on, when we saw through a microscope, I mean, inside this, the same diagram was available over here. So it was a treat for us to see that the same diagram is available over here and in the same fashion. So what you see in integrated circuit is nothing but a conducting layer and the transistor, which consists of the active area, the polysilicon area, and so on. So coming to the end, whenever you are going to design any sort of ICs, there are three challenges which everybody has to take care of, and those three challenges are called as SPIC. They stands for speed, power, and chip area. So if you are a designer, or if you are working in the IC domain, these three challenges everybody has to take care of, which means you have to design an IC which should be as fast as possible, which means speed should be as fast as possible. The power dissipation of that particular IC should be as low as possible. It should not dissipate more amount of power. And at the same time, the chip area should be of such a nature that it should occupy the minimum chip area. So I've given you the formulas as far as a power is concerned and a delay is concerned. So this is the diagram for, this is the equation for a delay, and this is the equation for a power. The power can also be further mentioned with respect to three quantities called as a dynamic power dissipation, or short circuit power dissipation, and a leakage power dissipation. So leakage power dissipation is also called as static power dissipation. So if you can see over here, the power dissipation depends upon a value which is called as VDD. So if you reduce the value for VDD, what is going to happen will be the device is going to dissipate lesser amount of power. So as a result, you might be knowing that nowadays the ICs which are coming up are operating even lesser than 1 volt. So if the power supply is a very smaller one, automatically the overall power dissipation will be a lesser one. And power dissipation, as far as the dynamic factor is concerned, also depends upon F clock, also depends upon VDD, delta V, and C. So that way, being a designer or being interested in fabricating some sort of an IC, if you are interested in designing some circuit which can have a lowest power dissipation, then these are the parameters which you are supposed to control. You can reduce the leakage current, you can reduce VDD, you can reduce a value for delta V, F, and so on. But at the same time, reducing VDD probably will have an effect on delay also. If you can see over here, the delay is inversely proportional to the value for VDD. So if you reduce VDD, what is going to happen? Of course, the power dissipation is going to be decreased, but at the same time, it will have an effect as far as a delay is also concerned. So all the parameters you cannot actually control. You cannot have a higher speed, you cannot have a lowest power, you cannot have a lowest chip area, and so on. Actually, you always have to make some sort of an optimization while doing that sort of the standard architecture. So the final conclusion as far as my talk is concerned is that the three greatest challenges in designing any sort of a product, particularly an IoT based system, is that you have to take care of speed, you have to take care of power, and you have to take care of the IC chip area. So the variable resolution ADC architecture we have already designed, and in that kind of a particular architecture, we have specifically used a binary search algorithm, or we have gone for a binary search architecture. And within that architecture, we have also incorporated the concept of reusability. So by using that sort of a structure, ultimately we have been able to achieve a variable resolution concept, which means for a signal, for a case or scenario where the signal strength is higher, we have actually designed the same circuit using a lower number of bits. And when the signal strength is a smaller one, we have made that same architecture for a higher bit resolution. So this variable resolution ADC architecture has been designed using the concept of binary search, as well as using the concept of reusability. So this particular work can have a special emphasis as far as home automation is concerned, or probably for certain cases where signal strength is a major issue. Probably in some sort of devices where you can actually incorporate the same feature with respect to going in a lift also, and with respect to the place where you are sitting on the top of the hill also. Now, in all these structures, comparator is something which probably is occupying the major amount of power. That is what we have experienced over there. So if we can design, or if in the future we can design some structures of A to D converters where comparator are as minimum as possible, then definitely we can save a huge amount of power. And to further design such kind of an architecture, already a binary search ADC is one of the potential candidate, and you can incorporate the techniques of AI and ML also in order to find out that which particular transistor can be switched, or which particular transistor which was not switched off in the previous stage can be utilized. So this is from my side, and thank you all for the patient listening. And if you have any questions, so I'll be very much happy to answer questions.
Any questions from the participants, please? Any questions?
So if some of you are working as a faculty member, so we already told you that we have a working professional program. So some of you can join us, and some of you can do a research also as far as these domains are concerned. So if any question is there, please ask me.
Sir?
Yeah.
Good morning, sir. Am I audible, sir?
Yeah, you are audible.
Okay, thank you.
You are audible.
Sir, actually, one small doubt I was having. Sir, actually, I have seen in some research articles that for MOS analog circuits, they are going to have output conductance. They are saying it is desirable to be low, but the transconductance it should be higher. So, sir, actually, this question I have asked in the previous sir also. But sir, I want to have more clarification regarding this, sir. If you can tell what is the basic difference between transconductance and output conductance, and especially in its applications purpose also. So, sir, if you could highlight this, please, sir.
Sure. Look, the value of transconductance, you already know, is given by the factor of rate of change of ID with respect to the rate of change of VGS. And normally, when a device operates, say, in saturation mode, or when a device operates in a triode mode, we can actually find out the value of the transconductance. So normally, it is proportional to the value of under root of beta I. Okay, and beta is given as mu c W by L, and I is nothing but a current. So that way, if you want the transconductance to be higher, then ultimately the value of the transconductance higher can be achieved by two quantities. Since it is proportional to beta and I, as a result, you can either increase the value of I, or you can increase the value for beta. If you increase the value of I, what is going to happen? The power dissipation will be increased. Okay, if you increase the value for W by L, automatically the chip area would be higher. So as a result, depending upon the application, as I have already told you in the slides, depending upon the application, only we can go for a higher GM, or we can go for a lower GM. It's not that always we go for a higher GM, because higher GM, the major drawback is that the device will become a little bit hotter, or the device is going to dissipate more amount of power, because it is directly proportional to the value for I. So depending upon the application, whether you want a lower power dissipation, or whether power dissipation is not your design criteria, then only you can choose a different value for I. a different value for GM. Is it okay?
Yes, sir. Sir, actually, why the name trans conductance? So, what is the significance of trans word here? Like we are having conductance, we are
Trans
having
means
trans
actually,
conductance. So, sir, actually,
I'll tell you. Actually, if you go by the formula, GM stands for ID upon VGS. Okay, so ID is your output and VGS is your input. So we are taking the output current and we are dividing it by the input voltage. Hence, it's a factor of Y21. Hence, it is basically a trans parameter. You might be knowing there are 4 parameters: Y11, Y12, Y21, and Y22. So Y21 is basically GM, and it is a ratio of output upon input. Okay, or how in general you can say that, you can put up in different way, that ultimately what is available at a designer's hand is input only. At whatever inputs you will be giving, what changes you will be getting as far as an output is concerned. So since it's a ratio of changing in the input and generating some sort of an output is concerned, hence it's called as a Y parameter, or hence it's called as a trans parameter or trans conductance parameter. Since the ratio is I by V, it's called as a conductance. Since the input VGS controls the output current, which is ID, hence it is called as a trans conductance parameter. I hope it is now clear to you.
thanks a lot, sir. Thanks.
Any more,
Yes, sir. Yes, sir.
Okay.
any more doubts from the participants, please? Any more doubts from the participants? Okay, sir. Thank you, sir. It was a wonderful session. It's my pleasure that I get an opportunity to interact with you, sir.
Thank you. Thank you.
You have
Thank you.
also explained about the Make in India, and you have also explained about the manufacturing units of the CMOS designs in 180 nanometer in the beginning only in
Yeah.
Mohali. It was
Yeah.
really is a pleasant surprise that India is also in a manufacturing unit of the Velisai design.
Yeah. Yeah.
And
And
also,
if you get time, then probably, I mean, some other time I'll show you the chips also, which we have received from India also. So
okay,
that is already there in the pipeline, and we at IIIT we have already received chips from I mean SCL Mohali.
okay, sir.
That work is already there. Yeah.
One question from my side also is there that below 180 nanometer, the CMOS, there is no manufacturing unit in India, sir.
Right now it's not there because actually if you go from 180 nanometer to 120 nanometer or 90 nanometer, the size will be a very smaller one. There'll hardly be a very small change. Okay, and I've already told you that the thickness of human hair is roughly around 100 micrometer.
Yes, sir.
So nanometer will be even 1000 times of that one. So even if you change 180 to 120, the size may not matter, but the investment will be huge as far as that is concerned. So already, government of India is planning that why not to have more number of ICs as compared to little bit going down onto that. So right now it's only 180 nanometer. It's not below 180 nanometer. But even if you fabricate an IC on 180 nanometer, probably it will be a huge advantage. And it's not that government of India is only for IT or IIIT or NIT or IITs. Anybody can participate as far as that particular program is concerned. So some of you who probably are associated with either of any of the INIs, or if you're interested in fabricating your own ICs, you can actually participate in that India chip program. So using that, anybody can fabricate an IC. Okay, and government is not going to probably charge also. There is already a program called a Special Manpower Development Program. So government is interested in generating manpower also. Already the semiconductor policy is there. So you will find that soon there will be huge opportunities as far as semiconductor market is concerned.
And so you have also explained about the design issues in designing converters. You have also explained the applications of the electronic devices in the field of Internet of Things. It was really a wonderful speech, sir, and wonderful session it was. And really, if anybody wants to go ahead with the research work in the Internet of Things related to electronic devices, they can make contact with the Professor Manish Goswami, sir. If you we will also uploading the video session, all the video clips of the sessions on the WhatsApp group, and also we are going to have the YouTube channel on the by the name of IERT, where we will be uploading all the videos. By today evening, you will get all the videos. And thank you, sir.
Thank you.
Thank you, sir. Okay, sir.
Thank you, sir.